Hi, this is Tim Szczykutowicz. This is 5-Minute Physics, and today we'll be talking about CT number. Can we trust it? By the end of the talk, I hope that you guys can learn this actionable information. Do not trust CT number when scanners change. Do not trust CT number when KV changes. Don't trust CT number when patient position changes. But if the ROI noise is equal to the mean, don't worry. You can usually trust that measurement. So first, what is CT number? Here's a typical CT image. Pixels represent attenuation. Places with low attenuation are dark. Places with high attenuation are bright. So for example, air, it's bad at stopping X-rays, so it gets a low attenuation value and a corresponding low Hounsfield unit number. For example, oral contrast is good at stopping X-rays, so it gets a high attenuation value and a corresponding high Hounsfield unit number. Here's some example Hounsfield units for different materials. Air -1,000. Oral contrast, a couple hundred Hounsfield units. Bone, depending on if it's a softer inside bone or harder outside bone, a couple hundred, about 500 Hounsfield units. Liver, depending on how fatty it is, what contrast phase, around 100 Hounsfield units. Muscle, a little bit less than liver in this example. So, we're not going to go into the physics of all this attenuation coefficient stuff, but basically the physics of what the attenuation is, we get nasty kind of measurements like 0.1865 or something like that for the attenuation of different materials. So what we do is we convert those attenuation coefficient values into Hounsfield unit numbers. And this Hounsfield unit then tells us how attenuating something is relative to water. We end up multiplying it by a big number, 1,000. That makes little changes between tissues into big changes, so we get nice integer values of Hounsfield units like -60, 5, 10, 997, etc. Instead of having to deal with these small little fraction numbers like 0.203 or something like that. CT number changes with vendor. So in a pretty controlled study, some authors looked at a rubber cartridge, a little piece of rubber. They imaged it in a bunch of different vendors, a bunch of different CT scanners, and they found systematic differences between the different vendors. The largest differences they found were about 40 Hounsfield units. But the rubber meets the road when you actually look at real patients, and another group did that. And here I've shown in red the unity line, and what we can see is none of these plots really follow those unity lines, and there's systematic differences between the GE and Siemens in this case for the same patients, same anatomical region measured. Their conclusions were Hounsfield unit measurements of unenhanced soft tissues in the abdomen varied between vendor, and this can result in mischaracterization of lesions. CT number changes with KV. All right, so there's that equation I showed earlier to get us nice integer values for Hounsfield units. Again, that's normalizing attenuation coefficient to that of water, but that does not take away the energy dependence of attenuation. There's photoelectric and Compton effects that happen inside of our patients, and each one of those has an energy dependence. So that what we see is, when we're looking at materials that have a lot of fat in them, like fat tissue, breast tissue, brain tissue, stuff with fat in it, it's going to increase Hounsfield unit with increasing KV. Whereas most other materials like liver tissue, bone, iodine, they decrease Hounsfield unit with KV. So here's what you need to know to pass your boards, right? As KV increases, CT number drops for iodine. Or another way to ask this is, you want to enhance iodine for a CTA or something, lower your KV. CT number changes with KEV. All right, so as the academic sites and the vendors keep pushing spectral CT on us, we need to know something about it. As we go down in KEV, most materials are going to see an increase in Hounsfield unit number for the monochromatic images. So even for materials that might not overlap at a high KEV, we go down to lower KEV, we get this enhancement in contrast, and we can see differences, in this case, between thyroid and parathyroid adenoma tissue. CT number changes with position. All right, so this is a study we did at Wisconsin, my institution, and even for the same scanner, same patient, you just move them up and down inside the scanner by clinically realistic amounts. You can see CT number changes over 20 Hounsfield unit just by moving them up and down in the scanner. So my ROI has a high standard deviation. Can I trust it? So here's an example of that. ROI mean is 15, standard deviation is 12. All right, Yes, because a lot of people confuse the difference between the standard error, which is a measurement of the variation of the sample mean, and the standard deviation of the pixels inside the ROI, right? So when we look at a PACS ROI, we're looking at the standard deviation of the pixels inside that ROI, not the standard deviation of the actual sample mean. So pretty much you get an ROI that's like 5 by 5 millimeters, 4 by 4 millimeters. Your uncertainty in that mean is only a few Hounsfield units. And this has been shown by other authors as well. Here, Davenport out of Michigan, your 5 by 5 millimeter, you're good to go for this particular indication at typical dose levels. All right, so we're 30 seconds over. Sorry about that. Thanks for joining today.